Ruby Community Conference done by Visuality, Ruby on Rails Experts Agency, presents Rosa Gutierrez, SolidQ internals, externals, and all the things in between.
So Marius has already introduced me. That's me. I work at 37 Signals. I've been there for 8 years, so quite a long time in tech. So I'm really grateful to be here. I love this conference. I was here a year ago in Warsaw for this same conference, the Ruby Community Conference, the winter edition. And as Marius already showed you, like me tweeting about it, I think this conference has the best ratio of talks versus all sorts of activities around it, and I love it because I love Ruby. I work with Ruby all day, but I think I love Ruby conferences more than Ruby, actually. So I probably, if I didn't work with Ruby, I will still try to go to all Ruby conferences because I think the Ruby community is the best. And yeah, I just love hanging with Ruby friends and people at the conference. So talks, presentations are super cool, but I know that the best part is when you get to chat afterwards and all that. So I hope we get to do that in the after party of today, for those of you that I didn't meet in the after party of the pre-activities. If not, tomorrow in the post-party, after party, whatever. So yeah, I hope we get to talk a lot. So the presentation I bring to you today is about SolidQ. So what is SolidQ? You may be wondering. So this is a new active job backend based on a relational database, unlike other very popular active job backends that uses a key value store such as Redis, for example. SolidQ was open source more than a year ago, so in December 2023. That was the very first version. Then we released the first stable version a few months ago in 2024. And finally it was introduced as the default in Rails 8 as part of the Solid trifecta. SolidQ is part of the set of 3 libraries that aim to replace the usage of Redis, Memcache, this kind of key value store with a relational database. Yeah, this was the post that announced the Rails 8 launch, and you can see that Solid Keyboard, Solid Cache, and SolidQ. About the why we decided to work on SolidQ, let me go back to some time ago in the conference in Rails World in Amsterdam, about a year ago, and I'm going to let my boss tell why we decided to work in SolidQ. So I think this is going to sound...
Following the same idea, we've started looking into creating a whole new job backend for Rails. Build on the same idea that if we don't need RAM for caching, why do we need it for queuing? So at Basecamp, at 37 Signals, we've been using Rescue for 10 years, 12 years, a long time. There's a bunch of other queue options in the Rails world that you can use. We looked at all of them when we finally grew tired of this. This is a number of different gems, and I don't think it even includes all of them, that we use to make Rescue run at 37 Signals. This is from, I believe, Basecamp. Here is 6 different gems to be able to do the interaction with jobs that we want to do. That's a mess. You should not need 6 different pieces to solve one.
Okay. So yeah, I'm glad that the sound worked because I wasn't sure. So I was rehearsing my imitation of THH talking so I could, do the talk. I'm glad because I still want to have a job on Monday. So I'm glad that this worked. So this is why we started working on SolidQ. So you've seen this video. This is this was the keynote in Rails World. This is on the audience. I was there. And yeah, I didn't want to look at that because I wasn't sure what he was going to announce or say or whatever. So he actually, after explaining the why, he promised that we probably will be launching this by the end of the year. And so the truth is that at that time, I was sort of struggling a little bit with motivation, procrastination. I hadn't touched SolidQ for several months, had been working on other stuff. So when I saw that, I was like, okay. So then, yeah, I automatically recovered all my motivation and started working. I call this methodology promise-driven development. And I really, really recommend it. Just when you're struggling, just get your boss in front of hundreds of people and promise when you have your work ready. So it really works. Okay, so now let's start with the slide with the 7 gems that he showed. So this was true. We've been running Rescue for most of our apps at 37 signals for quite a long time. And in the end, we grew to have these 7 gems to manage our jobs. And so you may be wondering, so why we have a number of gems that are done by the community. We have some forks of some gems, and we have some gems that we made ourselves. So you may be wondering, why did we need all this, right? So let's go quickly one by one to see why we need them. And this will give us an idea of what we have to build if we wanted to replace it with something new. So the first one, Rescue, is obvious. We need that to enqueue and run the jobs. Then we have this Rescue supervised fork. I don't know if you know, there is a gem that is called Rescue multi-fork that is used to reduce the overhead of forking every time you want to run a job. This is something Rescue does. So we're using Rescue multi-fork, so you could run multiple jobs just forking once. But the problem with that, with Rescue multi-fork is that if the parent of the fork process died in a very non-ceremonial, like not graceful way, you could lose jobs, like when the parent was passing them to the child. So we saw this happening a few times in production and that, so we made another version of that internally that we call Rescue Supervised Fork that handles this properly. So yeah, so obviously we don't want to lose any jobs, so that's why. Then we use Rescue Pool. This is a public gem that is used to easily run pools of workers. They are forked processes, so it makes easy to manage them. Then we have the Rescue Scheduler. This we used to run delayed jobs. Those are jobs that you enqueue to run in the future. Or, for example, when you use active job automatic retries, you can set the retry to happen like in polynomially longer time interval. So you need to be able to say, okay, run this job in 5 seconds or 10 seconds or whatever. So that we need Rescue Scheduler. And also for recurring jobs. With Rescue Scheduler, you can specify cron style jobs. So we use that. Then we have a Rescue Pause. This is a very simple one. It's just so you can pause a queue. Imagine if you are running into some trouble in production and a queue is causing problems, so you can easily just pause it and not consume any more jobs there. Then we have sequential jobs. This one, this is another internal gem that we developed at 37 Signals. It was done by my colleague Jorge, and it came up because we were in certain parts in our apps. We have some code some jobs that weren't that will run into problems if they run at the same time. Like, for example, imagine in Basecamp, which is a project management tool, a customer does an action that enqueues a background job that takes some time. For example, archiving a message that has many comments. So we will have to archive all the comments one by one, propagate that status, and that happens in a background job. But sometimes people will archive something like that, for example, and then quickly unarchive it, like undoing this in action. And that will enqueue another job to do the same, propagate the status. So those jobs running at the same time in parallel, it will cause a mess in the end. So that's a situation. We have, you could argue that this is a problem in our application. We should have solved that in application code properly, you know, but probably you are right. But the truth is that we have this scenario with jobs that will cause problems if running at the same time. We have this all over the place, like in Basecamp, in Hey, our email client. So for us, it was just easy to solve this at the job level. So we built a gem to just run some jobs sequentially. So to say, like, this job and this job, they cannot overlap. Like, they need to wait. So we have this. And then the last one, schedule job. This was also a gem we made in the company that was just to run some jobs that are scheduled in the far-ish future. We are talking about 30 to 90 days or so, just to have it there and to be able to enqueue them very quickly in batches. So this came up initially because we had an incident with our rescue setup where we were enqueuing many, many millions of jobs to run in the future, 30 days, 90 days from them. And what happened was that we fill up all the memory in Redis, in rescue. So that was a nightmare. We couldn't enqueue any more jobs. That was horrible. So we have to rethink how we did this. Like, you know, this. So this actually uses the database. This was a tiny, tiny seed for solid queue. And so what we did was storing all those jobs in a database table. And then do also some batch processing so we could enqueue those very fast. Yeah. So, okay, so that was the explanation of why we needed all those gems. And with that, we can summarize what we needed for a new, you know, the requirements for a new system that was going to replace this one. So, so when we, another requirement that came, because we thought, okay, if we build this, we'd like to start using it with our email service, Hey. And at that time, we were running with Rescue about this setup. We have about 650 workers with that polling interval, and we were running about 19 million jobs per day. So that's another requirement, like whatever we build needs to support this load. Okay, so then when we had this clear picture of what we needed, we thought, okay, what if we use a relational database, you know? Like we have recently, my colleague, Donald had shipped solid cache to be, which is an alternative to using Memcache or Redis for the Rails cache using a database. And he had successfully shipped it for Basecamp and for Hey. So that was working great for us. So we have this inspiration of replacing the traditional, more usual key value store with a database. There were also some very successful examples of using a database to run jobs, like Good Job or Delayed. We look into that. Good Job is really great. The problem is that it uses Postgres. It uses specific features that are only available in Postgres. So we couldn't use it because we use MySQL 37 signals. So we couldn't use a Good Job. We also look into what will it take to perhaps add that Good Job to run with MySQL, but it really is. It uses very specific features of Postgres, so it wasn't. And I even talked with the author. He agreed that it was going to be like shoehorning MySQL. That it wasn't a good idea, right? So anyway, so we thought, okay, what if we build a new one? That could be a good thing because we could leverage active record. Many all queuing systems are quite complex, because they were built not for Rails necessarily. They were built to be used with any Ruby application, so they don't use any Rails-specific stuff. But since we were going to use this only with Rails, we could leverage Active Record and have much simpler code, get things for free there. And finally, if we manage to do this, we will have just a fewer moving piece, right? We wouldn't have Redis, and we could just replace in Rescue all those gems and all that. So we will have a more simpler setup. And then maybe it could be a new Rails default, right? Okay, so if we wanted to achieve all this, to be a new Rails default, we have to first support the 3 databases that Rails supports officially. And we also needed to support all active job features as well, which in our case, that only means priorities. It was the only feature that we weren't using and that Rescue actually doesn't support. But if we wanted to, aim to be a new Rails default, we wanted to have, those 2. Okay, so you may be wondering if you've been using Ruby and Rails for a while. You may remember Delayed Job. This was a gem that was used to run background jobs using the database in the past. So why people started to, not using it or migrating to other solutions that use Redis like Sidekick or Rescue? Well, there is a problem with polling and in the database that is inherent to how this works. And let me show you how it works with, so usually when you have a queuing system with a database, what you have is you have a number of workers that are all the time checking a table for new work, because you don't have a way to notify, you don't have a PubSub system of sorts just to tell the workers that there is new work. They need to be checking the tables all the time. And what happened is that you also need to make sure you are not picking the same jobs multiple times. Like you need to lock those rows when you are going to pick a job to run. You need to lock it to make sure that you are the only worker that is going to pick that job. So if you are running a certain scale, usually you will have more than one worker working the same queue, not just one. So you will have multiple. So multiple jobs can be run at the same time. So what happens is that if you do this, you usually will have a query that could look like this. Imagine this is your job table, and you have this query. So this query, for example, imagine we have a worker running that. This is going to take to return the first 2 rows. And during this time, while this worker has these 2 rows locked and the transaction is still open, all the other workers that are polling the same jobs, they are going to be waiting, because they cannot do anything. They cannot pick those 2 rows because they are locked. So they need to wait until the transaction is committed. So imagine the first worker that got that will claim the jobs. For example, imagine that you can just set a Boolean there, and then it will commit the transaction. And now, only now, in the other workers, that same query that they're running, only then is going to return the next 2 rows, right? So you can see here that you will quickly run into a contention problem, right? Because the workers, basically, they will be waiting on each other. Okay, so now, how do we overcome this? So it was very easy. So since some time ago, there is this new feature in MySQL and Postgres that is for update skip lock. And this is very, very handy, because in this case, if we now, instead of using for update, we add a skip lock, it means that the one worker is going to lock the first 2 rows, and that is going to return them, so they will be locked. But now, the other worker that is running the same query, that query will return the next 2 rows immediately, because the first 2 are locked, so those are skipped, and it will just pick the next 2. So now it means that workers can poll without running into each other, without having to wait, so that's great. So that's the main idea. That's why we decided to give a try to this. And so we built a first prototype with this idea. So besides using select for update skip lock, we also try to do we try to keep the poll table as small as possible. Like your queries are going to be faster if the table you are querying is smaller. So what we did, instead of having just a huge table with all the jobs, like including all jobs that are going to run in 1 week that we don't need to poll now, and all the jobs that are already finished, and all that stuff, instead of having that, we decided to go with a different approach, which is just having a different table only with the jobs that are ready to run now. So that is going to be much smaller than all the jobs in the system. So in this prototype, we have different states for the jobs. We call them executions. And so, for example, when a job is enqueued to run in the future, we will create a scheduled execution there, so not in the ready execution table. And then, when that job is ready, because it's due, we will move it to the ready execution table, and only then it will be picked to be run. And even more, like when a job is already picked by a worker, we also remove it from the ready execution table, and we move it to be claimed. Okay, so we are basically the table is as small as it can be. It only has jobs that are ready to be picked. That's it. So this prototype had 5 tables. Only one of them had all the actual data of the job, the class, the arguments, all that. And the other tables have all the have just temporary execution data. So we will be moving, depending on the life cycle of the job, we will be moving its metadata from one execution table to the other. And then in our first prototype, we have 3 different types of agents. We have workers. They are just polling the ready execution table and picking new jobs to be run. Then we have dispatchers. They will also be polling, but in this case, the schedule executions and moving the jobs from schedule to ready. And then we will have a supervisor that will be just managing those processes. So yeah, what I say, like the dispatcher will move poll jobs to ready, and the worker will move poll jobs to claim. So just with that first prototype, we managed to check quite a few requirements. Yeah, we can enqueue and run jobs. We don't lose jobs. This came for free because of the databases and working with transactions. So the database guarantees that we are not going to lose any jobs if something happens, because we wouldn't be like, committing until we don't. We run all the operations, like take a job from a place, put it in another place. All that happens within a transaction. So you don't need to worry that. It's the database doing the work for you. And then we will have, thanks to our design with keeping the scheduled jobs separate, we will have also the inspiration from our scheduled job gem. We will have all the jobs in the future there without interfering with the jobs that are ready to run. And then we could also, this doesn't have any specific feature from any database. Like we are not using any specific, like both MySQL, Postgres, and SQLite all support this. We weren't using anything strange. So with the caveat that it needs to be MySQL 8, but it has been a few years already, so it's not unreasonable. And we also support priorities. We added that directly in the ready execution table. However, the design also introduced a new requirement, this design, which is not keep a job forever claim if a worker dies. This comes because we are moving jobs from ready to claim. So imagine that you move a job from ready, claim the worker, and then the worker dies. Like dies, for example, like someone goes to the machine when the worker is running and just pull the plug. So the job could stay there forever, claim, right? Because it's not ready, so nobody can use it. So we have a new requirement there. We need to do something, handle this case. So because of the architecture, what we did was to add a process registry, just to have a registry of the processes that are in the system, worker, dispatcher, supervisor, and have those workers, those processes send heartbeats. So we know, like if a worker fails to send a heartbeat, we know it may be dead, and we just go and release the jobs that are claimed. How did we implement that? So we just added another table. You will start seeing a pattern here. So we added a solid queue processes table. That's our process registry. We keep the heartbeat there. And then in the claim execution table, we just add a reference to the solid queue processes table. And that's it. And the supervisor is the one that is going to be checking the workers, the processes, the workers and the dispatchers' heartbeats. So whenever it detects that one of those processes has died, it will just take care of releasing the claim execution. Okay, so with that, we check that one. Now, this one, posing queues, this was a simple one. We just need to be able to say, okay, this queue is paused, don't poll any jobs from this queue. So yep, we just added another table, solid queue poses, very original name, and we just store there whether a queue is paused or not. As simple as that. And then this requirement, right? This was tricky, I mean, definitely harder than the poses queue. So what we did here was to allow this with our first prototype, didn't mention, but with our when we had the first prototype, we started migrating jobs to this system. So we could iterate over it. And we moved jobs that weren't user-facing or important, mostly jobs that did incineration. Like we call incineration when we soft-delete stuff in our apps. We don't delete it for real because, in case something goes wrong and people regret that they deleted something or whatever. So we keep stuff soft deleted. And then we actually delete it for real in the background. So that's the kind of jobs that we moved to solid queue in the beginning, because those weren't critical or anything. So with that, we were seeing that we were monitoring all the polling queries with our workers. We were running about maybe 20, 30 workers or so. We still saw that significant load coming from the polling that they were doing every second. Some of them were seconds, some of them were a few hundred milliseconds, but they still were loading the table quite a bit. So what we then focused was on further tuning the polling queries. So this is how the solid queue ready execution table looks like. So we have those three columns there are the important ones for polling, the ones that we care. The queue name, the priority to sort, and the queue name because each worker only looks at certain queues. And the job ID, of course, to fetch the job data. So, and the way we query this depends on the queue names. Like when you specify, I want this worker to work on the incineration queue, for example. So we need to look at how we wanted to specify this. Based on our rescue setup, we had some examples of workers running, for example, one single queue. We had other workers that were consuming jobs from different queues. Then for our beta environments, we like to specify a prefix. So we can say, okay, consume all the queues that start with this prefix. And then also the simple case, when you have perhaps a small app and you have a few queues or whatever, you may want to say, okay, all workers do all the queues. Okay, so we have to support this. And we also wanted to support post queues. So this is important because the way you select the way you design the query and the indexes, it matters how you are going to query the queue name column. Okay, so we'll see now. So what we did was to add those two indexes, and then do all our queries, restrict them to have this shape. That is either one queue name, just one, or none. So that. And if you keep your queries with those indexes, you keep your queries like this, so you are not, you never specify, for example, queue name to be two things or more than two things, or not in, like not just one, or no. If you keep your queries this way, those indexes are covering indexes, which means you can use them to sort. It doesn't matter that it's covering. Covering means that you don't need to go to the primary key and to the table to fetch more data, because we are only retrieving queue name, priority, and job ID. So those are covering indexes. And if you keep the queue name to be just one or no, you can use those indexes for sorting on the priority. So you don't need to do a file sort. So that made a huge difference. So yeah, so what I say that, so we have 0 or 1 per queue, per query, the queue per query. And then how do we do this? I showed you before that we wanted to support prefixes, multiple queues, all that. So what we do is we find how many queries do we need to run. In each case, for example, if you specify a worker with 2 queues, we will run just 2 different queries, one for each queue. And, or for example, if you have post queues, we will check first the post queues. If there is none, we will try to find the minimum number of queries that doesn't exclude that. If you have some post queues, we will find first all your queues, subtract the post queues, and then run 1 query per queue name. So anyway, it's all there, and we always do the minimum number of queries in total. Then with that setup, right now, we are running about 152 queries per second. And actually, before I did this, I changed those numbers before I did this. When I did this presentation in Rails World in Amsterdam, these numbers were way bigger. But I did a change recently that I haven't shipped yet, but some optimization on the number of polling queries you need. And we used to do about 4,000 queries per second, but now we are only doing 152. And then each query takes on average 180 microseconds, and they examine those rows, and that is very, very, very light. So with that, we weren't seeing the load we weren't seeing before, and we could easily scale this to the numbers that we needed for Hey. So that's it there. And then another requirement that was hard, it was remember the jobs that need to run sequentially, so not overlapping. This was tough because our sequential job, GEM, took advantage of really, really nice Redis data structure and features like having expiration, having Redis is super, super nice, has so many data structures that are really, really cool, and especially for stuff like logs and queues, like list or that, Redis is great. We didn't have any of that, and the problem was that all the ideas we have about not running jobs at the same time, not overlapping, they involve modifying how we poll, right? So how we, for example, imagine okay, these two jobs cannot run in parallel. Okay, so then with a worker, I don't want to poll this job, I need to exclude it. Then you start having to modify the polling queries. And what happened with the polling queries? That they were optimized up to the really, really to the chases, like really. So I didn't want to touch them because they were working, I didn't want to touch the polling queries. So I was very, wondering how to do this, actually. And I started first thinking, okay, what if first we make order not important? So just before, with our sequential job, GEM, order was guaranteed. So if you enqueue one job, then another, and they are configured to run sequentially, we guarantee that they will run in that order. But what if we make order not important? And the truth is that looking at all our usages of sequential jobs in Hey and Basecamp, there were only a couple of cases where order was important. In the other cases, will work just fine if they ran in a different order. The only important thing was that they didn't overlap. So what I did instead, so I'm going to modify the couple of cases that need the order and just make them, with a different application logic, to make them to make order not important there. And once I have that, I thought, okay, so what if we added, instead of limiting or restricting on polling, what if we do it on enqueuing? Like, okay, you cannot enqueue this job because there is another job that must not overlap with that job and is already enqueued or it's already running. Okay, so we try that, and we are using semaphores, which is, we implemented that in SolidQ. It's a very simple concept. So when a job is going to be enqueued, a job that has these restrictions, we check a semaphore for that job, and if it's open, we enqueue it normally. If not, we just block it. So we added a new execution type, block. And yes, that's another table. And we also renamed sequential because now, since order is not important, sequential is not really true. So we renamed that to concurrency controls. And this is how this looks in the initial prototype. So we added this new execution, and yeah, and we just tested it. So the problem with that, when we designed that and finished and started to testing it, is that this introduced quite a few more write operations on enqueuing, like when you are going to enqueue the job. Actually, in the worst case, which is if you have a scheduled job in the future that has concurrency limits, you need to do 11 write operations. Also, think that all the select for update, either skip log or whatever, those are actually write operations. So we need to, we have to do a lot of more write operations per job. So we look into how our job distribution of this kind look like, all our jobs that use this sequential restriction. We had a peak of 400 jobs per second, and we made some back of the envelope calculations with one of my colleagues in the SRE team. We saw our current database, which at the time, when we were running this, we were using the same database as our app database. So we have all our jobs, all our stuff was in the same database as the main app tables. So we have that, and we decided, okay, we cannot run this write load together in the same database as our app, as our main app. So we move SolidQ to its own DB. So that was also, a little bit laborious. But now SolidQ actually uses a separate database from the beginning. So if you install it and you start using it, you will get a separate database from the start, which is way, way easier than having to move millions of jobs when you are already using it in production. And also for SQLite, that is also supported, is also, I don't know if you know, but SQLite only allows it doesn't allow concurrent writes. So it makes all the sense to run your queuing system in a different database as your application, because otherwise you are going to be running into, so your queuing is going to affect the writes for your main application. So I think it's a good default. Okay, so we are done with that one. And then this one, cron-style recurring jobs that we also needed. Since we have limited time, I'm going to leave that as an exercise for you. A small hint, add some more tables, and you read them. Yeah, so besides that, we have a lot of, I told you about all the basics, the fundamental things, but there is a lot more stuff, you know, like all the bulk operations that we had before, log instrumentation that more libraries have, a lot of error handling, we have hooks, we have a dashboard to manage and inspect your jobs, and lots of bug fixes, cases, you know. And finally, to finish this, I'm going to show you, you remember I told you that if we started from scratch and did something new and simpler, we could leverage Active Record to make this simpler. And I don't know if you've looked into any active job backend or any queuing backend, like Rescue or others. They are quite complex. They do a lot of stuff. And I wanted SolidQ to be the opposite, like to be very, I mean, it has stuff, like it's not like it's super, super simple, but I wanted it to be straightforward. Like if you look at the code, you understand it easily, so you don't need to spend hours and hours trying to understand. So let me show you how the code to enqueue a job looks like. So this is the SolidQ job class. So we have there this enqueue method that just call create from active job. This just does calls create, the active record create method, and just copies, you know, gets all the attributes from active job, like the queue name, the arguments, the priority, and just copy them. And then the key feature here is this callback. So after create, we are going to prepare the job for execution. This is how those methods look like. So we have in the prepare for execution method, then we check if the job is due now, because when you enqueue a job, you can say wait until or wait whatever, so to enqueue it in the future. So we check if it's due, we will dispatch it, and if it's not due, we will schedule it to run in the future. And how is that schedule look like? It's just this. So that is your, you know, super common Rails code. And then if it was due, we will call dispatch. Let's see how dispatch look like. So it's here. So we have acquire concurrency log. This is related to the concurrency controls we have that will look like this. So if the job is not using concurrency controls, which is for most of jobs, this won't be the case, so we just return true, okay, the log is yours. And if not, we will use our semaphore class, which is very simple, you can look it up and wait. And then if we are successful in acquiring the log, we will just mark the job as ready. So that is how it looks like. It looks the same as a schedule, just with the ready execution table. And if we fail to acquire the semaphore, because the semaphore was claimed by another job, then we block. And yeah, that is how block looks like. So that's it. And we are, today, we are running, we use SolidQ exclusively for Hey, which is our email and calendar service. We run about 20 million jobs per day. And we are using about 400 workers. We are using less workers that we rescue. Actually, we shuffle things a bit and so that we could shrink the number of workers a little bit. We are using 4 dispatchers to dispatch all our jobs scheduled in the future, and 2 schedulers. The schedulers, I didn't mention that. This is a different type of process that we introduced for the recurring job thing. It's just they handle recurring jobs. That's it. Then for the user-facing jobs, we achieve the same latency, like they are running in the same time as rescue, and Then we also show us a speed increase when we are enqueuing in bulk, because with rescue, you always have to enqueue one by one, no matter how. Rescue doesn't have any bulk enqueuing feature, but we do have it with solid queue. So there we have some increase in speed, and then we didn't see any impact in response time. This is because, of course, enqueuing jobs in solid queue takes about 3 times more than in rescue. Like in rescue, if we were seeing about 1 or less than 1 millisecond to enqueue a job, with solid queue that will be 3-4 milliseconds, maybe 6 milliseconds in some cases. This is because obviously just writing to Redis is going to be way faster than having to insert in 2-3 tables in MySQL. That is always going to take longer. So, but the key here is that usually for us, we are not enqueuing jobs in GET request. Most of our job enqueuing happen in POST requests or PUT requests, usually in write requests. Those are usually slower, like than GET requests, because they are writing to the database anyway, and because we are not enqueuing tons of jobs. So maybe in some requests, you are enqueuing 2 jobs, or you are enqueuing 3 jobs, or 1 job in most cases. So a difference of 3-4 milliseconds there is not really impactful, considering that the whole request maybe is taking 200-300 milliseconds or so, like that request. So for the user point of view, it is slower, but it doesn't matter, because it's not really, like it's not, it cannot be perceived easily, so yeah. And so finally, just a small quote from my boss. So he said that good frameworks are extracted, not invented, though solid queue is a little bit invented, I suppose, and it's not even a framework, but anyway. So what I wanted to say with that is that the first version, the stable version we released, it's been really battle tested. Like, this is not something that we designed, we built, and we just shipped. It's something that we were building at the same time as we were using it all the time. Like every feature that we put there was first used by us in production, and so it's been really used by us, so it's not something. And I didn't really like so much the term battle tested. I prefer to say that it was being fun tested. We have this running joke in my company with the SRE team, where we refer to some stuff like, you know, PagerDuty waking you up at 5 in the morning, and we call this fun trademark. And so this has been really, really fun tested. And yeah, so help us to make it better. One thing that the community has been incredible is especially when it comes to other databases. I mentioned we use MySQL, a 37 signal, so we catch a lot of issues with that, but I didn't have visibility on problems that only happen in Postgres, for example. And I have a few great contributors point out issues that will only happen in Postgres and help me a lot troubleshooting, giving me clues, submitting pull requests and stuff, so this could be better there. In Postgres and also SQLite. So that was really helpful. Yeah, so if you can also help using it, testing it, and submitting issues, whatever. Yeah, and dziękuję bardzo. Yeah, and so yeah, I don't know if you've seen her, but I brought my dog there, and she's, you know, she's there. She's here, so if you, so I also brought some stickers, so just if you want some, come to me. And yeah, that's it. And do we have some time for questions, or?
Maybe 2 questions.
Okay, yeah, so.
Anyone? There is one, and here's one. You will tell.
Hi, I actually have 2 questions for me. So first, have you planned to check some performance comparison, especially for like Sidekick, for example? Especially, the second question is connected. So, in terms of in terms of, you still need separate instance of database, right? So how does it compare, for example, cost-wise to the instance of Redis that you need, for example, for a Sidekick, even in free tier?
Do you mean, so whether we have run, well, I haven't run any benchmark with Sidekick
okay.
because we don't use Sidekick, we've never used it, but there is benchmarks on enqueuing and running jobs. There is, I think Mike from Sidekick did a benchmark with solid queue with job, and I don't know if any more systems, but Sidekick is way faster, like way faster. I think Sidekick is the fastest by far. Enqueuing, executing, yeah. So I suppose it comes to the question whether how fast do you need it to be, right? Because yeah, it all depends on your needs, for sure. But I think I didn't understand very well. You say something about having a separate database.
Yeah, like this is a straight example, I think. So I want to set up Redis or a separate database for even same use case with Rescue. Which one is quite like cheaper, let's say, in terms of maintenance? Like your way of supporting separate database with ton of records, or actually having Redis instance?
I think it will depend on how you manage those. For us, setting a separate database was free, mostly, because we used Chef to manage all those instances. So for us, it was just running Chef and spinning up another database and just configuring it in a Rails application, because separate databases are built in with Rails. So that's basically free for us. But I think it will depend how you set this up. So for us, in our case, it's easier to set up a separate database because we need a database anyway for our app than having a separate Redis cluster to run the jobs. But I suppose it depends. Like you may be using Redis already for other stuff, so maybe it's the same for you. It's easier. What I would say it's been a big difference, though I haven't mentioned this here, but it's been a huge difference. It's been for managing the jobs. So I don't know if you've run into issues with jobs. We have like a long list of fun with jobs and with Rescue, and troubleshooting Rescue had been really hard. Like inspecting what is happening. You know, those jobs are failed. How do you retry those jobs selectively, perhaps? Like I don't know Sidekick very well because we don't use it, but actually Mission Control, the dashboard that we use for Solid Queue, we built it initially for Rescue because we have some issues where we had millions of failed jobs for any reason, and we couldn't really manage. It's really cumbersome to pick the Rescue data structure apart and operate over huge sets of jobs. So that was the initial reason we built Mission Control, was to manage this. So it's a huge difference if you just have active record objects in your Rails console and you manage that as you will be as you will manage any data in your application. So operationally, it's been really easier. But again, I don't know. I'm not really sure Sidekick how. Like the dashboard, I think it's super good. So if you're already using that, I think it's probably good. Yeah.
Okay, thank you.
Hey, I'm here. Yep.
Oh, sorry.
Yeah, it's fine. Thank you so much for your talk, and thank you for your work. I recently started a new project, and I really like how Solid Queue just work straight from the box, no configuration needed. It's awesome. Thank you. I have two questions, quite small. So first one is, I'm curious, would you recommend to anyone to care to move the Solid Queue database from from your primary one? Is the first one. And the second one, damn, I forgot it. So, I forgot it.
No worries. So your first question was whether I will recommend someone to move the Solid Queue to a separate database from the primary one in the app, because maybe you started using it before it was split, before version 1.0, so you are stuck with the same database, no? Or I will recommend it. Unless you have very strong reasons to run it in the same database, which some people do. Imagine you want to run you want to take advantage of the transactional integrity of enqueuing jobs within the same transaction in the same database as you are doing other operations with your app. So you may have that. It will be like advanced usage, that you know very well what you're doing. So unless you have that need, I will recommend to switch, to move it. But yeah, it will depend.
And now I remember the second question. So you have like 20 million jobs running daily, right? So I can imagine like you have like a lot of like space claimed by those, rows, right, in the database. So how do you reclaim this space? Like, do you like run like vacuum? And I can imagine like it can, do something like log something. So how do you handle this?
Yeah, so there is an option in Solid Queue which is enabled by default. So you by default it will store your finished jobs when they are run. So by default they will be there, and then there is a task that you can put it in the recurring configuration to delete all those finished jobs in whatever recurring interval. So that's what we do. We keep, I think, 12 hours or 24 hours, I don't remember, of jobs, and then we run a task every hour to delete jobs that were running before. And then with MySQL, you don't need vacuuming like with Postgres, where you delete rows are not actually delete, so we don't need to care about that. But I suppose if you are using Postgres, you will have this problem anyway for other tables. So.
Okay, thank you.
Thank you.
I know, Thomas, that you have a question, but it will be really probably difficult one, and long. So, yeah. So now let's make 20 minutes break. You can go upstairs, but let's see here